Okay, today we want to do the very last little bit of the structure of materials and move from there to discussion of the properties of materials. The things that I have yet to cover are fibers, lipid bilayers as an example, an organic material, a biological material, and quasi-crystals. Let me get this out of the way easily. We talk about crystal structure as being an organized, repeated pattern of atoms. There is another possibility in getting an organized, predictable pattern of atoms which does not involve the unit cell or direct crystallinity. And that creates a group of interesting, though utterly useless materials, which are called quasicrystals. An example of a quasicrystal is if you are tiling a floor, and instead of constructing the tiles in some regular repeated pattern, you start in the middle and do the tiles so that they just spiral out from the middle and form something like this. By describing for you that spiral, I could give you a formula that would predict where every tile was, even though the tiles are not in a repeated pattern. They are in a describable pattern. And that's essentially what a quasicrystal is. It's an ordered configuration of atoms that is not repeatable. It simply follows some non-repeatable pattern, usually emanating in some spiral-like or other geometric-like figure from some center of growth in which the quasicrystal begins. These were discovered 20 years ago, 25 years ago by a fellow named Shechtman, who was at that time at the National Bureau of Standards in New York, and in Washington. He's been in Israel for a number of years. And it was sufficiently exciting that on the fundamental level, that he actually got a Nobel Prize a few years ago for identifying these things called quasicrystals. They were very controversial when they were first discovered because there are ways to create things that look like quasicrystals by putting in periodic stacking faults into crystals. So there was a long period of time in which people argued that the quasicrystal was not a real state of matter. In fact, it does appear to be, and they exist in a number of systems. One of the most common classes of quasicrystals are certain phases that occur in aluminum alloys. The positive thing about quasicrystals is that they're very interesting from a topological point of view. They're very interesting to mathematicians and to crystallographers. To engineers, I cannot think of a single place that a quasicrystal has ever proved useful for any purpose. In fact, in every example I can think of where we encounter quasicrystalline phases, our first challenge is to get rid of them as fast as possible in aluminum alloys, for example, so that you can get good properties in the material. So that's what they are, and we won't need to say anything further about them. Fibers are things that are very commonly used, have been for centuries. The first fibers were used to make clothing and cloth and so on in prehistoric times, so they've been around for a very, very long time. They are increasingly used not only in sophisticated woven fabrics, but also in fiber composites, tailored structural materials that are becoming ever more widely used in aircraft and such things. There are really two classes of fibers. The inorganic fibers, like glass and graphite, which are the manufactured fibers that are used in fiber composites. Organic fibers, fabrics like nylon and so on, and things like Kevlar, which I'll talk about in a minute, which is what you make bulletproof jackets out of, with its own unusual properties. Starting with glass fibers, which are the simplest and the most widely used, and you see them just about everywhere. Glass can be drawn through a die to produce thin fibers. The major uses of those fibers in structural devices, they're usually chopped into short links and embedded in epoxy to create fiberglass, which you use around you all the time. They're also used in long links to conduct light as optical fibers. We will discuss both of these kinds of uses at the proper time later on in the course. The engineering considerations, the advantages of these glass fibers is that they are rather high in strength, they have good stiffness, good elastic resistance, and rather low density, so that you can make things rather light out of them. The disadvantage is that they're brittle. When I first came out here in 1971, I had blown all the money I had made in the stock market while working in industry and buying a fiberglass car, a Lotus Europa, which was a lot of fun. It was went to about 20,000 miles before it more or less fell apart. In fact, I was talking to buying it by a friend of mine and worked with an industry who was a former mechanic on a British racing team. He says, I want you to look at this car. He says, it's a classic British automobile, designed by a genius and built by British craftsmen who translate as idiots with 5 thumbs. He was an Englishman, so he was entitled to say that. And when I first bought it, I got halfway home and part of the roof fell out and hit me on the head. So tell me what it's about. It was a fiberglass car. The problem with a fiberglass car is that anything that fiberglass doesn't dent. If anything happens to fiberglass, it either scratches or cracks. And you can, in a very minor accident, get fiberglass damage that costs thousands upon thousands of dollars to repair, which is why you see very few fiberglass cars running around these days, even though it's a very light material. Yeah. Well, epoxy is just it's an organic plastic. Sure, it's polymeric plastic. Yeah. There are many. The reason I kind of double take answering your question is there are many things which are classified as epoxies, many different formulations, but they are organic plastics, which I'm not sure if it's true of all of them or not, but in general you have a two-component system that reacts to form the epoxy, and you can therefore just make the epoxy in situ. Form it out. Fiberglass it almost always has epoxy as its matrix. The problem is, of course, these things are very brittle. They break easily and can cause lots of problems. Graphite fiber is much stronger. We talked briefly about graphite fiber earlier. If we have a sheet in the graphite phase, the sheet is very strong and very stiff in the plane of the sheet. Of course, in ordinary graphite, the sheets are just stacked up, so there's very little mechanical integrity in the graphite itself, and it's used as a lubricant. But if I take that sheet and roll it up, it's like a newspaper, I get a fiber which is very strong and very stiff. And this happens naturally in certain processing of fibers. When we just take certain organic fabrics and pyrolyze them, that is, just heat them up until they decompose and leave the carbon behind. With the right process, you get this thing naturally. We'd in fact been making carbon fibers for quite a while before anyone realized that this is what their structure was. They used to make very strong, stiff composites. They are strong, but again, unfortunately brittle, and very weak in the perpendicular direction. If you load fiber particles side by side into a composite, you have great stiffness and strength if you pull along the axis of the fiber. But if you pull perpendicular to the axis of the fiber, you're basically testing the properties of epoxy, which are not very good. So it's a very directional material. My personal funny story about this, my father was a golf professional. And among other things, he built the golf course at Patrick Air Force Base, which was Cape Canaveral, at the time that the astronauts were down and we were first going into space. And of course, at that Air Force Base, lots of these high-tech pilots came out, and they were all into the very latest technology. One of the first applications for graphite epoxy was to golf club shafts, specifically drivers, because that's a uniaxial, a golf club shaft is taking a centrifugal force, it's a uniaxial load, and it's very light, very stiff, and so they made very good drivers. So all these hotshot pilots would go buy these graphite drivers, which at that time, this was in the mid-1960s, cost $500 a piece, which is equivalent to maybe $6,000 now, $5,000, something of that sort. So these were enormously expensive. Well, these fellows were all by their graphite drivers. They go out to the golf course and everything was fine until they missed the ball slightly and hit behind it, at which point they would have two graphite drivers, only one of which had a hit on it. And so there was much weeping, wailing, and gnashing of teeth in the first use of these graphite drivers. Yeah.
They still bend more than steel, right? Because I've seen some like golfers use it, and it's like a stick bends.
Well, whether it bends or not, its specific stiffness is much higher than that of steel. Whether it bends more or less than a steel shaft just depends on the geometry of the shaft.
It bends like kind of like along the central axis of the shaft, right? That's what
No, and actually, it's very stiff along the axis, so there will be very little stretch. No matter how hard you swing, very little stretch. But perpendicularly, yes, it will bend. And how much it bends, the flex of the shaft, is a design feature of the shaft. And you control that by using the property of the material, but then controlling the geometry. Since the graphite is so stiff itself, you can you can get a certain stiffness in the shaft at much lower weight than you would get with a steel shaft. And so many people prefer, these days, most drivers and fairway woods and such things have graphite shafts. An awful lot of professionals prefer steel shafts in their irons because they feel it gives them greater control. It just is a matter of taste. It's, I used to be a decent golfer. Now I'm not good enough to tell the difference. So anyway, this is the graphite fiber, and this is the basis of that graphite fiber. Yeah. Well, of course, this is used in aircraft. The most modern aircraft are finally using these. Let me say that when I went to work in the aerospace industry in the late 1960s, the graphite fibers had just hit. And it was an article of faith that immediately all aircraft were going to go to fiber composites. This is now 40 years later, more than 40 years later, and we're just now beginning to see actual commercial aircraft making heavy use of these. There were many, many challenges. I'll get into those challenges later on in the course when we're doing structural materials. But a huge promise, and like many things that happen in engineering, the promise is obvious. The problems don't become obvious until you actually try to do something with the material, and then you discover what the challenges are. And that was certainly true of graphite fibers. Yeah.
So these graphite fibers, for something like automobiles, you see for the chassis, the main body, like a carbon fiber titanium alloy. How does something like that work?
I'm not sure
How to form something?
I'm not sure what kind of car you're talking about. Which is that?
They use, are that specifically, they were using some carbon fiber titanium alloy?
You might for some kind of specialized racing cars. I'm not that up on the technology right now. The Corvette, for example, has been a fiberglass car more or less forever. The Lotus was, I think, still is. I haven't been able to afford a new one. This is fiberglass. When you start getting into graphite composites, you're talking a lot of money and a lot of engineering. So while there may be some race cars that use a significant amount of fiber composite construction, I'm not aware of any commercial vehicles that do. And it would surprise me a little bit because you would shell out huge sums of money for it. But it's very expensive too. Sure. Yeah, as was the Lotus body, and that's both an advantage and a problem. It's an advantage in that it saves you a lot of weight. It's a problem then if you start a crack at one end, it tends to run through the whole car. In the first composites used in aircraft would be fiberglass with the underbelly, because the underbelly of an aircraft really doesn't do anything. It doesn't serve much of a structural function. But they ran into some real problems. If, for example, a baggage truck runs into an aluminum underbelly, it leaves a dent. A baggage truck runs into a fiberglass underbelly, you've got to ground the plane until you can replace the underbelly. These have been the problems of using those materials. However, the weight advantages can be, particularly in aircraft, where you, as we'll discuss later, you end up talking about specific properties, modulus over density and such things. The weight advantages that you can achieve with these composites are really formidable. So it has been worthwhile to continue beating on the technology until they finally appeared to solve most of the problems, and we now have large commercial aircraft that are very heavily invested in fiber composites. Kevlar. Ironically, when I was interviewing for a job right after getting out of school, I interviewed both DuPont and Phillips Petroleum down in Oklahoma, and both of them were at that time in the process of inventing Kevlar. Both of them described it to me in kind of mysterious ways because they didn't want to tell me what it really was. And neither one was aware that the other one was working on it. So I ended up going to work for a company that was, one of the things we did was partly was with armor. And so we started dealing with both of these companies, and I think we were the first person to told them that they were both working on the same thing. But Kevlar is really very interesting stuff. This is what you make the bulletproof vest that people wear these days. They're not quite bulletproof. Let me describe what Kevlar is and how it works, and then I'll tell you some of the good and bad sides of bulletproof vests. In Kevlar, you have benzene rings that get joined together in kind of a planar array, except the array is not quite planar. The bridges that connect the benzene rings cause them to become kinked. So you wind up with a sheet of material that looks kind of like an accordion folds, and therefore it has considerable elastomeric stretching in this direction. When you do these properly, and I do not know the details of the manufacture of the Kevlar fiber, but when you do it properly, you end up with a structure that looks something like this. These accordion folds end up radiating out from the center of the fiber. So you basically have a fiber which consists of radiating plates with these accordion folds. And therefore you can pull on this fiber and you get considerable elasticity. You can actually control the modulus of elasticity depending on exactly how you make the plate arrangement with these puckered sheets. This also has the advantage that while it has some stretch associated with it, a considerable stretch because of these accordion folds which can be pulled and flattened out, when you get to the limit of your stretch, you're left with this very strongly bonded benzene sheet. And so after you stretch these things out to almost flat, suddenly it becomes very strong and very difficult to break. Now this is, I'm getting into the theory of armor right now, but there are two ways to stop a bullet. You can stop it dead, which is what we do with ceramic armor, or you can catch it, like a catcher's mitt. And that's essentially what Kevlar does. When a projectile hits a Kevlar barrier, the Kevlar gives with the projectile, slowing it down, and then it's eventually strong enough that the projectile will not penetrate, and therefore it's rejected, and you therefore don't get shot. The problem with this approach, it produces a fabric that has the advantage of being flexible. If you've ever tried on a Kevlar jacket, they can actually be fairly comfortable. So it's easy to wear, unlike a ceramic armor, which is unbelievably uncomfortable, believe me. And you can put these on, you can wear them, they do protect you. The problem is that in the way they protect you, you do not get shot, but you can get a hell of a bruise from the impact of a bullet coming through Kevlar. Just like if you've ever had the misfortune to be a catcher for a pitcher who can throw a 90-mile-an-hour fastball, you catch the ball, but you come away with a swollen hand when the game is over. And this method of protecting yourself from projectile does have drawbacks, and that's you can really get hit pretty hard with a projectile, which will not penetrate, but can leave a really bad bruise behind. But that's this kind of fiber. I guess that's enough to say about fibers. We'll return to that subject when we get out into the mechanical properties of materials, and of course, optical fibers will cover under optics. The lipid bilayer is the one example I'll give you of a biological membrane. As I said earlier at the beginning of the course, Material science is one of those fields that over my professional career has changed really dramatically. So much of that has come because of our ability to see things, our characterization techniques, and our understanding of what's happening at a fundamental level in what is really a very complicated problem, because we control the properties of materials by controlling microstructures. The microstructure is the pattern of all the atoms, and that's something we can only in rare and ideal cases fully describe. So there's lots and lots of room for new understanding and new manipulations and so on. The field of science that has progressed perhaps even more dramatically is that of biological materials. And here, really for the same reason. At the time I entered college, there was not a course at MIT that referred to the structure of DNA. It had been discovered, but nobody really knew much about it yet. Now we do all sorts of things by manipulating biological materials. Again, because we have over the years found ways to characterize those materials, to understand them, to see reactions that we didn't really know about before. And here too, we're not talking so much about how we manipulate the materials as how God manipulated them beforehand. So they have these fascinating properties that we have to dig in and find the structures. But it's basically the same issue. We're dealing with materials that have very complicated microstructures. Those microstructures enable them to do things that are very, very useful. And the science is to characterize the microstructure and to understand how it accomplishes the processes that it does. And because the field is so complicated and the microstructures are so difficult to fully characterize and describe, there is lots and lots of room for improvement. And it's going to be that way, not only for what little is left of my professional career, but for the whole of yours, I promise you. New things will be discovered one after another after another. I'll just take the lipid bilayer as an example, because this will be known pretty well, at least in its overall outline. A cell wall, such things, is made of a bilayer, a layer of molecules back-to-back that forms a surface. This surface becomes the site for all sorts of things to happen. Biological functions, many biological functions are controlled by this cell wall or the cell surface. It captures things, it absorbs things, it repels things. It is the site for the biological reactions to happen. And it's very brilliantly and actually very simply constructed. The basic building block of a lipid bilayer is the phospholipid molecule, which has here's a picture of it, courtesy of the National Institute of Science and Technology. It has a head and a double tail that sits down here. The important thing to recognize is that this head is polar. It has a strong polar moment. The tail down here is nonpolar. It's basically just CH2, basically just a carbohydrate. So we end up with a molecule that has a polar head and a nonpolar tail. Such molecules appear in many places in engineering, and they're very useful because the polar head can let us attach to things, other polar things. The nonpolar tail is relatively inert. To give you one quick example, the best organic lubricants have precisely the structure. The polar head attaches to the surface and keeps the lubricant as a nice thin film over the surface that you want to lubricate. The nonpolar tail essentially just provides an inert surface that doesn't really want to attach to anything, so you get rather low friction. So lubricants are designed this way. Well, in the lipid bilayer, you use this in a slightly different way. If you throw this thing in water, the polar head really likes water. It's hydrophilic. The nonpolar tail doesn't. It's hydrophobic. So if you throw a bunch of these molecules into water, what they want to do is the following. They want to form a bilayer. If you're in water and these get together and organize themselves in this way, as illustrated here, then the polar heads on both sides of the membrane are in contact with water, and they like that. The hydrophobic body can exclude water, and it likes that. So you get this nice bilayer that forms very naturally, organizes itself with no trouble, and comes out with a very nice film. The chemical power of this film is also in the structure. If you throw anything else into the vicinity of the cell, if it's polar, it will tend to bond here to the surfaces. If it's nonpolar or hydrophobic, it will tend to be sucked up here into the bulk of the membrane. So we have things that go naturally to the surfaces and react there, things that go naturally to the bulk, and even more, we can take other molecules, proteins, which are copolymers, if you want, with hydrophilic segments and hydrophobic segments. The hydrophobic segments will get trapped in here, which locks the protein into the membrane. The hydrophilic segments will be dangling out here in the walls and can therefore interact with whatever they want to interact with in the interior of the cell. So this is a very potent little device for fixing chemical species and accomplishing chemical reactions. Of course, these things would like to organize themselves, to crystallize themselves at low temperature. If they were to do that, it would be a catastrophe, because all of your cells would have very brittle walls and you would not be here. However, because these are nothing more than carbohydrate chains, and because they have a complex internal structure, being double chains, they do not organize themselves very easily. So while the bilayer will freeze, will essentially crystallize at very low temperature, at temperatures of the sort that we inhabit, it's rather disorganized in here, and as a consequence, the membrane is flexible. Just going back to this kind of thing, you see all kinds of reactions going on here in the membrane. You have things that are attached to the surfaces, and being attached to the surfaces of the membrane, they're available to perform reactions there. The membrane can serve a catalytic function of bringing these complex molecules together and letting them interact. You have things that are buried in the interior, and you have things that are trapped in the membrane, but have segments that protrude out. Here's an example, here's another. So these proteins can be fixed by the membrane, and their reactive segments fixed in space. So there's a great deal of chemical flexibility in this simple little membrane. There's a couple of examples. Proteins absorbed on the surface can perform catalytic functions. Being absorbed on the surface, they contact other proteins and interact with them. Proteins that penetrate the wall. A classic example are the channel proteins that allow a nerve to fire, for example. What happens in that case is